for a SAIFR summer school in January back in 2001 or something like that. They were very proud of having had one day in 1946 where it actually snowed, so there were stores selling winter wear all over. And the weather here is a little bit different today. Anyway, I want to tell you about some work that I've been doing in combination of people, starting with Chris Pope and Ben Crampton, and then going on with my more recent students, Alex Harold, Chris Erickson, and Rahim Lung. And also there's ongoing work with current students. So the question is how, well, you have these, what we call brane solutions, generalized membrane solutions in supergravity theories. And can you do anything useful with them? So this is what we call a taxonomy. There are different types of boundary conditions. If you have a higher dimensional system, which you want to, you have a background solution, which we're going to call a brane, generalized membrane. So it's a solution of supergravity where there's some special subsurface, right? Where something more interesting than elsewhere happens, like a world volume. But it's only worth calling a world volume if something actually happens there. So there are two types of boundary conditions if you separate variables. You separate variables and you'll have modes going in what we call the world volume, and then transverse modes. And so you have to do this general separation of variables process. And you analyze this by looking at the transverse problem separately, which becomes a Sturm-Liouville, an eigenvalue, eigenvector solution. And then there are two types of situations. That's what we call the taxonomy. The first one is what in dimensional reductions, but this isn't a reduction. We're not actually reducing. We're letting the transverse space be out there, but looking at what happens when you look at the fluctuations with these two different types of boundary conditions. One thing you can do is a kind of consistent truncation, which basically means really limiting the fluctuations to only happen in the lower, what we call world volume dimension. In a standard, say, circular or toroidal dimensional reduction, that just means nothing depends on the extra coordinates. And that is naturally consistent in the sense that any solution that you have on the world volume, you can rewrite as a good solution in the higher dimension. That's a consistent truncation. Now, the one thing we found is that you can also do this on brane solutions where it's not compact. There's really an infinite amount in the transverse direction, but you can still have consistent truncation. This isn't like a circular or toroidal reduction because there is structure in the transverse dimensions. It's a brane. So there are fields that are falling off as you go towards transverse infinity and so forth. There's a whole structure there, the background solution. The consistent truncation is don't mess with the transverse, right? Leave it fixed and only give excitations in the world volume. And what we've been finding is that there are certain circumstances where this happens. We call the transverse structure then a skeleton. We don't do any excitations in the transverse directions. We excite only in the world volume directions. And the long story is it works in certain circumstances. And in fact, if the background solution has supersymmetries, this extends, in fact, to a full supergravity theory in the lower dimension. That's type 1. On the other hand, these are second-order differential equations. The type 1 boundary condition is basically don't mess with the transverse dimensions. That's one boundary condition. But in second-order systems, there's going to be another interesting, maybe interesting solution. Another solution in any case may be interesting. And that's the other type of taxonomy, which in fact in some circumstances gives a full localization of gravity phenomena near the underlying brane. This will not be a consistent truncation. That means that this type of setup eventually uses the entire higher dimensional theory, but it can have behavior that localizes and looks at effectively, at least for a certain range of energies, like a lower dimensional theory. So there's differences between these two setups. Okay, so that depends upon the choice of boundary conditions for fluctuations. One example is what we call, when you have a brane world volume, there's a Part of the calculation, of course, in finding the solutions to the higher dimensional theories, you calculate the Ricci tensor. The quiet brane background will have a world volume where the world volume metric is just flat, A to mu nu. But there's a generalization of that, and I don't want to go through the details of it, but instead of having flat, it works to have the world volume be Ricci flat, and it still is a good solution of the higher dimensional theory. Okay. Now, and moreover, if there's a surviving supersymmetry, as I've just said, then you can extend that to a supergravity theory. So instead of just Ricci flat gravity, you can extend it to a supergravity. That's, again, type 1. I don't want, maybe, you can go through this in an example, but because I probably have too many slides, let me just mention, if you work it out, basically what I mean by this situation where you don't mess with the transverse dimensions, you have this ansatz for the metric with warp factors A and B in the world volume and the transverse dimensions. And you see, then you have these structures for the Ricci tensor in the full theory. And if the A and B fields, functions satisfy the same relations as they do in the quiet background solution, and all you do is change these Ricci tensors, and they vanish, you see you've done nothing here, and then the solution goes through. Again, I don't want to go through the full details of that, but that's the type 1 configuration, which generates a consistent reduction to a supergravity in the lower dimension. It's not a compactification because the transverse directions are compact, and like I said, it's a skeleton, so this is sort of a smearing in the sense that as you go way, way, way away from the world volume, there's sort of a copying of whatever you're doing on the world volume. If you're putting ripples down there, there are ripples copied in higher dimensions. That is type 1. It's a way of getting an effective theory in the lower dimension by just saying, I don't care about the transverse directions. And the important thing mathematically about this is that it works. It generates a full, consistent solution of the higher dimensional theory. Okay, now, this again is what I've said, is about the preservation of supersymmetry, generalizing that to supergravity. Now, I don't, again, let's not maybe go through the details of this because I have quite a lot. I want to talk about the type 2, or rather, a system where you can either have type 1 or type 2. Again, because of second-order differential equations, you'll have a choice of which boundary conditions on the transverse dimensions, a part of the solution, you decide to adopt. So back in 1984, there was a construction by Abdesalam and Ergin Sezgin, and your parent institution in Trieste. There's a version of a 6-dimensional supergravity, minimal. That means in 6 dimensions, it's chiral supersymmetries, 1, 0. It's coupled to a 2-form tensor multiplet and a super Maxwell multiplet. Now, there's an R symmetry. Are people here familiar with some of the terminology of supergravity theories? R symmetry is a symmetry that basically rotates the fermions of the theory. It's a rigid symmetry that associates with the supergravity theory. It's not gauged. But in this case, this Maxwell multiplet says, oh, vector field symmetry, I'd like to gauge it, please. Okay, so that's what they did. It gauges the R symmetry in that case. What you get when you do that is, in the 6 dimensions, this Lagrangian. Okay, you have the Ricci tensor for gravity. You have the vector field for the Maxwell multiplet. The tensor multiplet, of course, has a 3-form, it's 2-form tensor, and it has a 3-form field strength, which, of course, now involves this this sort of transgression mixing with the 1-form of the Maxwell multiplet. And there's a scalar field. And the important thing is this last term, there's a potential for the scalar field. It's this sort of exponentially falling scalar, which means that scalar is not going to be happy sitting at any quiet constant value. It wants to slip, slip, slip. So trying to take the scalar to a constant value and looking for a maximally symmetric solution to the rest of the theory isn't going to work here. The important thing I want to note is the sign of that. Of course, this is in an action. kinetic minus potential, that's a positive potential. That's very unusual in supergravity theories, right? That gives rise to a possibility, which you generally don't have. You can do a dimensional reduction, look for solutions which look like lower dimensions, and in fact it is, again, in this case, a consistent reduction. That's against a type 1 situation. You can't do it on a torus because that's flat, because the scalar field likes to slip away along its exponential potential. But you can do something with curvature. In fact, you can just put a humble sphere. And in fact, because you have a nice two-form here, sorry, you have the two-form field strength, actually, and that is an attractive thing to give rise to a value, constant value, with epsilon mu nu value on the sphere. If you have a two-sphere reduction from 6 to 4, maybe you can get home. And the four-dimensional solution there can be flat. Normally, when you reduce on a sphere, you generate a lower dimensional theory which has an anti-de Sitter geometry, negative cosmological constant. But you started with a potential, with a positive sign, and the two can cancel each other out. So actually, there is a solution here, which they found, where you have a nice four-dimensional flat space, and then the sphere, and then you have the one form, the gauge, the Maxwell field, and now the scalar, because it has these two compensating pieces, one coming from the sphere, one coming from the potential that was there, it is happy to sit at a constant value, which by adjusting notation we've set to be 0. Okay, so that's the Solomon-Sezgin vacuum. It generates a four-dimensional, lower dimensional world volume. In fact, it preserves 8 unbroken supercharges. And so what I said about having a lower dimensional supersymmetry, you can do that here. Now, no, it gets its other part because of the tensor multiplet. Yeah, it would have been for 1, 0, but the tensor multiplet gives rise to it's another 3-form, the other half. Yeah, that's important the way it works. Well, like I said, this actually, well, I haven't said it yet, but I'm going to say it now. That, moreover, can fit into not only 6 dimensions, but you can go all the way up to 10 or 11. It is part of a type 2A or M theory in 11-dimension setup. And so this will be a situation where the world volume is going to be 4-dimensional, and you have to lift it, so you have to find a way to write all the extra dimensions, and this is the way it works. So now these are higher dimensional. This is, for example, to lift it into type 2A in 10 dimensions. And the various extra dimensions start to show some interesting structure when you write it this way. One way of viewing this is a dimension. Well, where did that positive sign come from in the potential, right? Normally, when you dimensionally reduce, you generate anti-de Sitter type things. This is a situation where you generated the potential that would have wanted to create an anti-de Sitter type thing in 6 dimensions or other dimensions where you land. It actually has the opposite sign. That's an indication that whatever happened between this 6-dimensional theory and 10 dimensions is not a usual dimensional reduction. It's in fact a reduction on a non-compact space, which is called H22. It's a 3-dimensional space of, can be embedded into 4-dimensional Euclidean space with a constraint that goes plus, plus, minus, minus, right? 1 squared plus 2 squared minus 3 squared minus 4 squared equals a constant. Okay, so that's non-compact, and that actually is how it works in order to generate that scalar potential. Anyway, in 10 dimensions, that was basically the way that Miriam Svetish, Gary Gibbons, and Chris Pope lifted it. Then you can rewrite it this way. You can reorganize things and discover other things. Going from 10 to 6, I just talked about H22, which is actually a 3-dimensional space. That takes you from 10 to 7. If you want to reach what was in the literature called the Salam-Sezgin starting point, there's another dimension you can reduce, which is just an ordinary circle. So that's this Y. And then you have this, so then you have this part here is interesting. This ds4 squared is in the transverse directions, and actually what you recognize it is an old friend that showed up. There's Iguchi-Hansen. It's part of the solution when you write it now in this 10-dimensional perspective. So that's just nice because you see an old friend, but it actually turns out perhaps to be an important part of the story. So that's how you can lift it up to 10 dimensions. And, as I've said, there are unbroken supersymmetries, and in fact, you can then, if you make this type 1 reduction, now the skeleton is what I just wrote for you, you can now consistent fluctuations around this background, and it generates a supergravity, n equals 2 in 4 dimensions, 8 supercharges, off the Salam-Sezgin skeleton. So that this suggests, in fact, that such consistent truncations may be a general feature of such supersymmetric brane worlds, and we're starting to see this in other circumstances. I think it's a theorem, but we don't know how to prove it, that this always happens. When you have a brane solution with unbroken supersymmetries, not only can you decide to let the metric on the world volume be flat, or generalized to Ricci flat, you can extend that to a supergravity with the extension of supergravity be whatever's unbroken on the quiet skeleton. Okay, that was mainly about what I call type 1. Now, there is a second order set of transverse differential equations, and you can look for other interesting solutions. Now, you could look for solutions where you're not so concerned with consistent truncations, but really just whether an effective theory of lower dimensional physics shows up. You're going to run immediately into a problem when you try to do this. So just take your brane background and shake it. Shake, rattle, and roll, right? And look and see, does it behave like a lower dimensional theory anyway? And there was a problem that Hull and Warner identified way back in 1989 for reductions on non-compact spaces, which is that if you look at the effective Newton constant that you would have for fluctuations around a brane or any solution with a non-compact transverse space, the effective Newton constant turns out to be 0. Why? Because in the general formalism for Newton's constant as a function of the dimensional reduction, you have the Newton constant in the higher dimension divided by the volume of the transverse space. If it's infinite, bang, Newton's constant vanishes. Another way of saying that is actually it doesn't behave like a lower dimensional gravity at all. It behaves still like just a higher dimensional gravity. And the 1/r potential that you might be anticipating for the Newton's constant ain't there. You get a different power depending on the actual higher dimensionality. Okay, but you can get around that. One thing to note, however, even for what I just said about these consistent truncations, hey, wait a minute, I was talking about supergravities there. They have all sorts of interesting interacting solutions within the supergravity. What happened? What happened to Hull and Warner's critique? Well, the answer is, as in general relativity, there ain't no Newton's constant anyway. It doesn't mean anything, because classically, these theories have a scale symmetry. I think I'm guilty of inventing the word trombone symmetry from some sort of Dizzy Gillespie moving around with an extension, right? The point is there is a scale symmetry of the equations of motion, but not the action. Pure Einstein theory, with equation r mu nu equals 0, has such a scale symmetry. That means you can make a scale transformation. You go from one solution to another good solution. Are we familiar with this? Yes, you bet we are, because actually that generates a family of solutions where an integration constant associated with this symmetry arises, and it's called the black hole mass. That value, black hole mass, the integration constant, is in fact changes from one to another when you make this trombone transformation. That generalizes in supergravity theories. In order for the scale symmetry, this trombone symmetry to work, the various terms in the action, they're not invariant, but they have to transform homogeneously, all with the same scaling properties. Pure supergravity theories all have that feature. So when you dimensionally reduce to a pure supergravity theory with extendant of various extension of supersymmetry, it still works like it does just for pure gravity. Okay, so that is to make Hull and Warner not worried about it. You should be careful about trying to couple to anything else, however, because that's where Newton's constant would really come in. So the Hull and Warner problem is sort of pushed away to coupling to other stuff. Okay, so let's go and try to study generally fluctuations around a brane solution like this. And it happens, in fact, that if you're interested in spin 2, gravity itself, this problem of studying the fluctuations is easier than you might have thought it to be, precisely because instead of worrying about all the indices on the Einstein equation, if you're studying spin 2, the transverse part of the solution doesn't have any indices left. It's basically a scalar problem. So in fact, what you have to study is the behavior of the scalar D'Alembert in the higher dimension. You write it out this way, the standard trick of taking the second order, the D'Alembertian, right? Take the derivative, raise the index, make it into a density, then the covariant derivative of a density is an ordinary partial, and then take the density away. And in fact, then you can split that up into a four-dimensional D'Alembertian, a thing which which involves a bunch of angles here, which are sort of naturally compact, and actually for simplicity, because we're lazy, we're actually going to set the dependence on those to 0. Those are sort of natural Kaluza-Klein dimensional reductions. But there's one coordinate that's important, which is a kind of a radius. We called it rho, and that's where this delta, this is where the actual important dependence on the extra dimension comes up. It's given here, d squared by d rho squared plus 2 over tangent 2 rho d by d rho. There's a warp factor here that comes out in front. And so that's how you rewrite the 10-dimensional D'Alembertian, and you now have to pull this apart and, of course, now separate variables into fluctuations on the world volume and transverse modes. So here we go. We propose, say for a scalar field, x's will be world volume coordinates, and like I say, because we're lazy, I only gave you rho. Right, there are all these other angle coordinates I've set dependence onto 0. We don't need any angular momenta in these extra higher dimensions. The simplest, in any case, they'll naturally be quantized, so those will give you even higher energy solutions. We want to look at the lower energy ones. So there'll be maybe some discrete modes show up. So that's what this sum is to start with. Functions of the x's times a set of eigenfunctions depending only on the transverse coordinate rho. And then, because of Hull and Warner, you anticipate a continuum of transverse modes by the integral. Okay, so we can have maybe discrete modes and definitely a continuum. Okay, so the omegas give rise to the Kaluza-Klein masses that you'd see in the four-dimensional space. And actually, you would be disappointed if you have to deal with a continuum of four-dimensional masses. Sometimes we're going to talk about that, but the interesting case would be if there's a nice single discrete mode which does what you want, generates a lower dimensional gravity. It'd be even nicer if there's a mass gap so that you don't have to worry about the continuum until next week, or whenever you get an accelerator big enough to thump it hard enough. And let's set all these other coordinate dependencies to 0. So this is the problem, you see. You have to solve that del psi is minus omega squared psi. This is the Sturm-Liouville problem. And then you have a four-dimensional D'Alembertian with masses g squared omega squared, mass squared. Okay, so now let's look at this particular case for Salam-Sezgin. It turns out to be convenient to redefine the transverse variables xi by taking out a factor square root of sinh 2 rho, called as psi's. That makes the relevant transverse Sturm-Liouville into a clear Sturm-Liouville problem of everybody's familiar with from quantum mechanics. So this is classical, but it's still a Sturm-Liouville system with a certain potential here that comes up. Otherwise, this is like a time, the time-independent Schrodinger equation. Now this potential is given here, 2 minus 1 over tan squared 2 rho. You say, well, did I see that anywhere? Yes, people who have a good education in quantum mechanics or who've read all the footnotes in Landau and Lifshitz will notice, hey, this is a special case. The problem of falling to the center or something like that, they called it about. It's a Puschel-Teller potential, and Teller is the teller of the H-bomb. This is before he left Austria, and Puschel, I think, was a woman colleague of his. If you look at large rho, you can see that the solution, that equation limits to this. And you can see, of course, they're going to be a continuum, which we'll call these scattering states. But for omega squared greater than 1, and here then are the scattering states, standard exponent e to the I and e to the minus I extensions, solutions for this again for the large rho dependence. For omega squared less than 1, there can be an L2 normalizable bound state. And recalling the rho dependence of the measure from the 10-dimensional measure, it turned out to be this. You find that for large rho, you sum over take some value far, far out and go out to infinity. And this is where the test for normalizability is going to be. This condition can converge for psi squared. And in fact, it requires the falling real exponential. Because the complex exponentials are there in the continuum, and you can have a falling real exponent. You threw away the rising one. Okay, so you can have a candidate bound state, and you know where to look, where this separation variable omega squared has to be less than 1. And if you can find one, then you can have a mass gap before the onset of the continuum. And in fact, that's what happens here. And moreover, there's a nice value of the bound state continuum, which is called 0, which means that the corresponding supergravity on the lower dimension is actually going to be purely massless. The lower dimensional gravitational mode are going to be Pauli-Fierz theory. And moreover, you can actually find that mode explicitly, given here. And then the excitations of the world volume, now times this psi 0, around the 10-dimensional lifted Solnit-Sezgin background, correspond at linearized level to massless 4-dimensional gravitons in the 4-dimensional world volume subspace-time. So this is a localization of gravity on the world volume. You can test whether this idea really works by doing it. Now, this is it's actually what we call type 3. I don't want to go into type 2. It is the localization type of taxonomy. It is not a consistent truncation. So all the solutions here are still really solutions of the higher dimensional theory, but they behave like solutions in the lower dimensional theory. What do I mean by behave like? Well, I don't know where it is in Sao Paulo, but in London we have a hill called Crystal Palace where all the TV antennas are and so forth, and everybody, actually, this generation doesn't know about antennas anymore because you just get it out of cable out of the wall, but your grandparents used to know about antennas. If you go a long way away from an antenna, you have a nice clean signal, right? If you go right up to Crystal Palace, there are not even any good cafes up there, but there's a nice walk around there. The field is just a horrible mess, right? The difference between near field and far field. When you have this sort of localization, what you hope to happen is that you get far enough away from a source, it behaves like lower dimensional physics. If you put a source and a test particle close to one another, in this situation, you expect to see the higher dimensional physics reestablishing itself. So what you have to do is to study the green function. The green function in general is going to contain a term involving the Xi0. By the way, one thing about this Puschel-Teller system, this bound state, there's just one. There's only one bound state, and then there's a gap, and then there's a continuum. They're not two bound states, just one alone, which is nice. Okay, so that's why you have this C0 squared in the green function, and then a continuum contribution from the edge at 1. So you have to now study this, and this is where my student Chris Erickson, actually he's gone on to do things in the computer industry. We tend to have this problem in London with bright students who defect from us to go and make money with it and have a real life instead of being academics. But he sort of sleeps with Grashstein and Rizhik under his pillow. Right? He knows all these special functions by heart. And so we could actually do some summations here. I'm not going to go to the, well, here, let's go. Did I do that? Yes. Sorry, where am I? Here. Yes, so, yes, here's the green function. The near field behavior, press on the wrong button. The near field behavior looks like this. It's a higher dimensional behavior. By the way, it's like I said, I was lazy, and I got rid of all these extra angles because, you know, why? There's those you can make standard Kaluza-Klein dimensional reductions on. So we're not going to see 10-dimensional behavior because we squelched it. That corresponds to 4 of these angles, which are sort of naturally compact. There's one extra one in there which we suppress the dependence on because we're lazy, but actually that we probably should have remembered. It's still an S-wave solution, but actually this near-field behavior, when you look it off, squared to the 3 halves, that looks like cubed. Where do you see that? It's not 2 dimensions, not 4 dimensions, it's 6 dimensions. Where did 6 dimensions come from? Well, the reason we have the rho, transverse coordinate, and actually, remember Iguchi-Hansen, it's a nice smooth thing, it has a nose. And at the tip of the nose, which is where the brane solution is, it flattens out. There's an R2 living there. That contains a radius and an angle. So by suppressing the chi dependence, it's fine for getting these solutions, but actually we should remember that actually what we're going to generate is a 6-dimensional near-field behavior, and that's actually what we see. If you want, you can restore all the other angles and see 10 dimensions, but then you just get a lot of complicated formalism without learning anything especially new. So near field, it does restore a higher dimensional behavior. Far field behavior, when you analyze it, and this involves knowing how to sum over the modes, and this is where Chris Erickson and waking up at 3 in the morning, reading page 325 of Grashstein and Rizhik or whatever, you realize he knew how to do it. You find that actually what you get, it's dominated purely by the 0 mode and 1 over R behavior. So it's a classic evolution from a far field behavior that looks lower dimensional. As you come closer into the antenna field, you start to see a higher dimensional behavior. So that's actually what you would think this should behave like in a natural localization, not compactification or truncation. This is the other type of an effective theory of lower dimensional physics coming up with the lower dimensional Newtonian structure, but for far enough away, source and probe far enough away. Let's see, where are we? How much time when did I start? I'm not quite sure. Okay, so again, now, in order to find more general examples of this, and this is something that I did with my student Hong Lu, who also I lost to the financial industry. It keeps happening again and again and again. But you can study this from a more general context of Sturm-Liouville problems, which actually was started by Hermann Weyl back in 1910. And we found a modern treatment of this in an American Mathematical Society monograph by Anton Zettel, who actually seems to be working on Sturm-Liouville problems with singular boundary conditions in quite detail. So there's some language. Again, I don't want to go through the detail of this, but one, first of all, rewrites, so this is like the transverse problem, right, which is the Sturm-Liouville problem, rewrite the second order differential equation in this form with a certain, this involves choosing variables such that you force it into this form. C is the eigenfunction, prime's first derivative. P is a certain weighting factor, and mu then becomes a measure, and the measure is what you want to use in order to check L2 normalizability. This peak C prime quantity, which then gets a second derivative, is called the quasi-derivative of C. And the transverse coordinate here basically is what I call rho before, but more generally they called it Z. Thank goodness I'm finally to the west of the Atlantic. I can call it Z instead of Z. I don't know. In Brazil, what do you call it over here? Anyway, I have to remember which country I'm in when I speak. From 0 to infinity. So now, so the singular endpoint is, there's a certain terminology that Zettel and others, starting with Hermann Weyl, introduced of limit circle and limit point. The reason for limit circle, you basically have to go back and look at Weyl's paper. But so there are these two different types of behavior of endpoints, 0 and infinity, the interesting ones. And it's limit circle if all solutions to the given Sturm-Liouville problems are square integrable with respect to the measure, mu, in a neighborhood of the endpoint. Not all the way, but just in, this is a local issue around the endpoint. And if it's not limit circle, it's limit point. And then Zettel says that all solutions to this Sturm-Liouville problem for a particular eigenvalue are square integrable for some integral in between I, a subset of 0 to infinity, then it holds for every lambda. So the dependence on the eigenvalue drops out for this classification. It doesn't actually depend upon the specific eigenvalue lambda, although initially you might have thought that it would. So this is a sort of a global story about the Sturm-Liouville problem. So now, now that you can do it independently, the eigenvalue, obviously the nice one to look at is 0, right? Look at eigenvalue 0. So now you can obtain the 0 modes directly by integrating, remember the quasi-derivative, with the 0 eigenvalue, and you can find that P comes in the integral part, and there's also going to be a constant. So there'll be constant and non-constant transverse modes, and the condition for the z equals 0 endpoint to be limit circle then is that both of these conditions have to hold, where some non-constant k is just you limit the integration only up to k, don't go all the way up to infinity. So this is a condition around 0, and similarly at infinity. If you can't get both of these to converge, then it'll be limit point. So for the brane world examples that admit world volume gravity localization around 0, z equals 0 is either regular or limit circle, but the point at infinity, I remember we had to throw away that rising exponential, we didn't want that. So that it's going to have one solution that works out there in order to be integrable. That you anticipate. It's also possible for it not to work at all. So, then you introduce a certain notion of a bracket. The reason for going through all of this is that actually one has to characterize the boundary conditions that give rise to this localization phenomenon. And the self-adjoint extension, now, by the way, this is the story, I don't know about you, but when I learned differential equations as an undergraduate, second order differential equations not too bad and so forth, self-adjointness. And then there's an asterisk and a footnote about real self-adjointness as opposed to just hermeticity. And I said, oh, that's too complicated. I'll deal with that some other day. This is the other day. This is where you have to pay attention to all of that fine print at the bottom of your math textbook. So that's where Zettel's book was very particularly important. So we find actually, using these brackets, that in order to get a self-adjoint set up, you have to impose not Dirichlet, not Neumann, but a combination. which is called Robin boundary conditions, with a particular boundary condition set here, where we use the this Zettel bracket. Okay, so we have a condition and a language, and there are no special conditions other than L2 normalizability at the infinity limit point. And the key required information that you need then is the limit circle point at z equals 0, z equals 0. Okay, now the spectrum is going to be a subset of the eigenvalues, be a subset of the real numbers, and can be a union of two disjoint sets. Basically, the discrete spectrum and the continuous spectrum, which are called the essential spectrum. And then you can characterize various cases. C0 is going to be self-integrable. The essential spectrum consists of real numbers where the basic solution are not square integrable, but they can be delta function integrable. So this basically corresponds to the distinction in quantum mechanics between bound states and the continuum. So in the cases that we are interested in, where z equals 0 is either regular or a limit circle, and z equals infinity is a limit point, and indeed, we see the essential spectrum doesn't depend upon the particular boundary conditions on the specific self-adjoint realization of the Sturm-Liouville problem, but the discrete spectrum does. Once you're into the continuum, it's basically delta function normalizability, and it's not very complicated. But for the discrete cases, you have a certain lower limit of the essential spectrum, that's the continuum, and then you have a number of cases where, depending upon where that is, if the lower limit is minus infinity, it's just a real number, then the essential spectrum, that's the continuum, can be the whole real line. Or it could be discrete closed intervals separated by gaps. And then you have the other case, which is C0 is in infinity, and there's no essential spectrum. So the spectrum of every self-adjoint realization is purely discrete, and they're only bound states. Or you have something in between, some point with the edge of the continuous spectrum somewhere between minus infinity and infinity. And then the point sigma 0 is called the oscillation number. For eigenvalues less than that, every non-trivial solution has either no zeros or a finite number of zeros. And if you're above that value, then each non-trivial solution has an infinite number of zeros. Okay, now orthonormality. Basically, it's going to be the condition here involving that bracket that you have to have a zero bracket at z equals 0. The bracket has to vanish. C0 is the zero eigenfunction. This, of course, C0 itself, because it's an antisymmetric condition, automatically satisfies that condition. The question is about all the other eigenvalues. In particular, if you have the one bound state and then the continuum, you have to have this work for all the xi lambdas in the continuum. And okay, so now we find the normalizability condition here. It involves that measure mu that I mentioned. In fact, in general, different eigenvalues, you should get a Kronecker delta, and the scattering states will be delta function normalizable. And in fact, this condition, the one for the discrete states, is an easy way to see which eigenvalues are allowed in the discrete spectrum. So if you have an eigenvalue, two different eigenvalues, and not equal to 0, one of them not equal to 0, you can use a little algebra here using the bracket condition. And you can see, in fact, that that, in fact, just reduces to a condition of the bracket at 0 and infinity. And if they, what I call those solutions obey the star condition on the previous slide, then the condition at z equals 0 is satisfied trivially. So for the condition for orthonormality, it just involves the condition at infinity. for all pairs of eigenfunctions with unequal eigenvalues, one of them not equal to 0. So only the asymptotic behavior solutions at infinity is required to check whether they belong in the spectrum. Okay, so that's a bunch of mathematics. Okay, now back to some practical examples. One of them that you can write in terms of this language is Randall syndrome. People know about Randall syndrome too. Basically what they did is not really a reduction, but they took anti-de Sitter space in a certain set of coordinates where they basically folded it over. They just took the expression for the anti-de Sitter metric and put an absolute value sign in. And that's their background. It's a kind of a brane solution, which therefore at the location where they flipped it over, it requires a delta function, and then there's a talk about a volcano potential and so forth. There's a whole history of Randall syndrome, which I don't want to go into. But instead of going through it in that language, we can push it into this Zettel type language here. And here is what the Sturm-Liouville problem for the transverse part of Randall syndrome looks like. And so this is the starting form of the transverse equation. You can rewrite it in the sort of Zettelish form with P, given this way, Z plus 1 over K to the minus 3. Mu, in fact, is the same as P. The endpoint Z equals 0 is regular, but Z equals infinity is singular and is limit point. The zero mode solution, well, in fact, one is a constant, and the other is this quantity. Again, second order differential equation, two solutions. So you have this Z plus 1 over K to the 4th power. That's the non-constant part. And when you multiply by mu, you find it's proportional to 1 plus Z plus 1 over K to the minus 3. Sorry, for the constant part, because that's entirely mu. And for the non-constant part, it's Z plus 1 over K. So this C0, in fact, is square integrable in the neighborhood of infinity, but the non-constant part is not. There you have, out of the two possible solutions at infinity, one of them passes the normalizability condition, the other one doesn't. So this is what we call limit point. The zero eigenfunction is the constant mode, and it's around that that you generate the effective theory in massless gravity in the lower dimension. The general Randall syndrome's Sturm-Liouville problem is given this way. Now, okay, if you want to know what the solution really looks like here, you get involved in Bessel functions, J and Y, the first and second kind. They're oscillatory for all eigenvalues greater than 0. So the essential spectrum, in fact, starts at 0. Starts at 0, and there's a 0 mode that's normalizable. There is no mass gap here. There's a normalizable 0 mode, and then the continuum comes smack down right on top of it. So then a natural question is, does this really localize? It does. It does in a particular way, which I'll come to in a little bit. Okay, so for lambda less than 0, they're not square integrable, so we throw that out. They're not part of the discrete spectrum. And the self-adjoint domain solutions are given here with the J's and the Y's. That's Randall syndrome. I'll come back to that when I mention that in a little bit. I want to focus more on Salam-Sezgin, which in fact had these two taxonomies, which are interesting. So we come back to this equation, which I've already given you, the second order differential equation, and you can write it into this Zettel form with the bracket with P equals mu equals sinh 2z. The endpoint at 0 is limit circle. Z equals infinity is limit point. The 0 modes are given by a constant part and a non-constant part, the log tanh here. Now, around 0, they're both square integrable. That's by limit circle. But it is, in fact, the non-constant part happens to be is a singular one, so it's treatable by, it's in fact not very singular, it's just a logarithm. But it is, it fits into this Zettel classification. So we have Z equals 0 as limit circle. The constant mode, on the other hand, is not square integrable out at infinity. So that's the one you throw away. You want to keep the non-constant mode, and you have a limit point situation with one still good eigenvalue, but you have to take the non-constant one here. To deduce what the essential spectrum is, you have to look at the asymptotic form. Well, in fact, I just did this, right? You have had solutions with, I wrote it exponential rising and exponential falling, or you can rewrite it into sines and cosines. They're oscillatory for lambda greater than 1. That's the edge of the continuous spectrum. The essential spectrum is from 1 to infinity, and the oscillation number is the lower limit of the sigma, which is 1. To deduce the discrete spectrum, you look at the boundary condition, remember, called star at z equals 0. This bracket with the square root of interval 0 eigenfunction is given by here, this, our old friend, C0. And the boundary condition given here is, this is the row-bound type boundary condition. Okay, so that is Randall-Sundrum and Salam-Sezgin localization written in this language. Now, the general solution, well, if you want to write the general solution, you get involved in Legendre function, special functions, and so forth. Okay, so I'm not going to go through the detail of this, but because Chris Erickson loves these functions, we went through it in some detail. Now, there's a single bound state, as we've seen, and the orthonormal solutions to the Sturm-Liouville problem in the self-adjoint domain are given as here, involving the Legendre functions Q. Okay, now, that was the example that I talked about before, but rewritten in terms of this fancy Hermann Weyl, Zettel type language. The fancy language is useful to us, actually, for looking elsewhere, seeing can we find any other systems that work like this. And we found a number of examples. Of course, Randall-Sundrum fits, as I just said, and Salam-Sezgin. And then we found a number of cases involving D3 branes, not a simple D3 brane. You can't just take a D3 brane. That's a Dirichlet 3 brane, 3 plus 1 dimensional, 4-dimensional world volume. That one doesn't localize gravity. But if you put a D3 brane on one of these what are called resolved spaces, and again, for time, I don't want to go through the details of it, resolved conifolds of various sorts over S5 divided by Z3, or the YPQ spaces, or T11 over Z2, then it works. And gravity is localized in these cases. So there is a wider family of these types of localization of gravity. Away from, aside from Salam-Sezgin, which I've talked about, these have a certain structure which may in fact be general. They have an asymptotic R2. Remember the nose of the Iguchi-Hansen. There's an asymptotic R2 times compact directions structure as you approach the brane world volume. And this gives rise to the logarithm. Remember, the Laplace equation in 2 dimensions is a logarithm. That's where that came from. It's from those 2 dimensions. It's the nose of Iguchi-Hansen. So is this completely general? Well, this is what we found. And so we found it by using this Fessel language. Okay. What about these situations where there's no mass gap? Okay, what about Newton then? Does this just ruin the system? No, it doesn't. Again, this is something I won't want to go to in detail, but you have a potential which is going to have to involve an integral now over the transverse eigenfunctions. And because if there's a mass gap, you can see that the lowest continuum eigenfunction is going to generate Yukawa-type potential corrections. They're exponentially suppressed. So there will be a near-field, far-field behavior, but in the far field, the first correction other than the lower dimensional Newtonian 1 over r structure is going to be exponentially suppressed because of the e to the minus lambda r over r. If you don't have a mass gap, you should worry about that. And you're going to have to deal with an integral over contributions to the potential all the way from 0 to infinity. Now, if you happen to have Chris Erickson as a student, and he wakes up in the middle of the night and does sums using Grachstein and Rizhik, you're okay, and that's what we found. In fact, we did a detailed analysis of that for the Salam-Sezgin setup. But for these ones going to 0, Chris Erickson unfortunately graduated. So what you can do, however, is look at limits. So, in fact, you can see per mode, you're going to have a Yukawa type correction, but you have to perform this sum over modes. And going through, so this correction that you have to see, what one can see by a certain analysis, similar to some of the discussions that I've given you, is that this, the important part of the contribution from the continuum is going to be limited to the values near 0. Once you get away from 0, you're really going to start dealing with Yukawa type exponentially following corrections. So you can put a cutoff to that integral, and we like to call it epsilon squared. So let's integrate from 0 to epsilon squared, and then you can see what happens as you do a number of things. Take epsilon approaching 0 from the upper side. Go far, far out, because you're interested in the far field behavior. Remember the antenna farm discussion. Go far out. You want to see if this looks like lower dimensional gravity. And then, but hold epsilon squared r constant at some value less than infinity. And then you can see that this integral, in fact, turns out to be proportional to the square of the 0 mode as a function of transverse variables divided by r squared. Aha. And then that, of course, has to be inserted. Remember, this is the integral of everything, except there's a 1 over r, 1 over r, 1 over r squared. And in fact, you find that you are generating a, you're generating a 1 over r cubed leading correction after the Newtonian 1 over r. And that's exactly what happens in Randall-Sundrum. It's not an exponential suppression of the corrections, but it's a power law suppression. And they behave rather similarly. Okay, so that's basically what I wanted to tell you about. There's an overview here. That so basically the two taxonomies. They give rise to, first of all, the type of brain world consistent Kaluza-Klein reduction with a fully interacting brain world supergravity possessing the same supersymmetry as that of the vacuum brain, which serves as a skeleton for the Kaluza-Klein ansatz. This is a consistent reduction, but it's basically a smearing of the brain world fun and games on the world volume, copied, 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 smeared in all higher dimensions without change. Versus the other type, which is the full localizability, which is not a consistent truncation, but it's fully localizable in that it generates an effective theory in the lower dimensions. It's really a full higher dimensional solution, but it behaves like lower dimensional physics. It requires a normalizable transverse wave function 0 mode, like C0, and then that requires a specifically modified choice of near brain boundary conditions, this Robin boundary condition. This gives rise to a fully self-adjoint transverse Sturm-Liouville problem with a single normalizable bound state 0 mode in appropriate geometries, as we found a number of examples. And that's basically what I wanted to tell you about. One thing I'm aware about here is this is all classical, and there are police out there, the swamp police, right? And I don't know if any of this can be generalized to string theory, which probably, from my point of view, is maybe the quantum theory of gravity. But it's because it really involves genuine non-compact transverse spaces. I think the standard theorems and so forth that sentence you to the swamp are not applicable here. But Qumran Vafa may come around in his patrol boat and kick us out anyway. what can I say about that is, exploring a little bit Sao Paulo yesterday, today I got completely messed up on buses, that's why I wasn't here for lunch. And yesterday, we also got messed up on buses. We were going on the right bus, but we went in the wrong direction. We were trying to get to the Museum of Brazilian and African Art, which we eventually got to late in the afternoon, but instead we went downtown. And then I found this, some hope for solace in the Sao Paulo Cathedral, which I found remarkable. I don't normally go around cathedrals, but I found this this beautiful stained glass. And look at this. This is a cathedral that's celebrating science. This guy's got a telescope in there. I've never seen anything like that in a cathedral. Normally, normally all the various stories of the Bible and so forth, but this is something rather sophisticated in Sao Paulo that I didn't know anything about. Maybe just because in order to get here, you got to have good navigational skills, because otherwise you're not going to find it. So that's why there's a globe there. But I thought this is rather cool. So anyway, I have no idea at all whether this saves us from the swamp, but I can see there's some hope for an appreciation of science in this culture, and that's why I wanted to come to talk to you all here in ICTP in Sao Paulo. So thanks for your attention. Okay, supersymmetry in this sort of what we call type 3. It's part of a longer story. This is not a consistent truncation, so the supersymmetry that is there is the higher dimensional supersymmetry. I think in the effective theory, you're going to have similar zero modes for the superpartners corresponding to the other modes of a would-be supergravity theory. But it's not a consistent truncation, so that this actually, the statement that you have in a consistent truncation is you have a playground in the lower dimension for type 1, where you can do anything you want. You can thump the ground as hard as you want within that theory, and it's still a good solution in the higher dimension. In this case, the supergravity is going to be only effective in effective theory. If you thump too hard, you're going to wake up the higher modes, or you'll wake up the higher Newtonian corrections and so forth. But yeah, with the unbroken supersymmetry, there are going to be similar copies of this analysis for the partner mode. So it's useful, this comparison of the two taxonomies, right, of the consistent reduction, which is really a lower dimensional supergravity, except that it's smeared, versus the localization, which is not smeared, is really localized, but if you hit it too hard, it's going to wake up the full higher dimensional structure, and that should permeate to the other partner modes too. Yeah.
Related to that, do you expect that the supersymmetry of this low energy below the gap will be the full supersymmetry, or is maybe?
I think it's going to be primarily a symmetry of the preserved supersymmetry of the quiet solution. So you have the static sleepy skeleton, okay, without any excitations. That supersymmetry that is unbroken in that solution is what's going to give you the effective supergravity extension in both cases. But in the localization case, it's not an exact dimensional reduction.
The reason I ask is because of, this looks very nice, I thought, for applications to the real world, right? I mean, Branes and Sturm, they were just trying to find some, effective idea for the real world, but now you have something that comes from gravity.
Yeah. So there's a point that one can make about Randall-Sundrum, which is their transverse space isn't really non-compact, because what they did is, in a certain set of coordinates, is they folded over anti-de Sitter space, and in folding it over, they threw away a part of the space-time. Actually, they threw away the infinite part. What they kept was a finite part, written in coordinates that makes it look like it's non-compact, because the coordinate goes from 0 to infinity, but it's actually fully compact. So the localization of gravity in that case is easily understood and that's all I want to say. It's not really a non-compact. The title of their paper was an alternative to compactification, but it's not really an alternative to. In these cases, I think they really are genuine non-compact localizations. The brane transverse space is, I mean, if you look, there's not a finite proper, world line going in the trend. Unlike Randall syndrome, it really is infinite. So it still can happen, and it happens either in the Randall syndrome case thanks to this special property of the Purcell-Teller potential, or in these other cases where they're Randall syndrome-like, but still with non-compact structure.
I think really it would be much better from all points of view if you can find something that actually breaks supersymmetry 20 to 1. That would be ideal, because people were looking, I know for a long time people were looking, where do we find Randall syndrome in string theory, and then he found that you can go down some funnels in compact space and so on. But with this would be, if you can break supersymmetry, this would be completely well defined.
Okay, all right. So there's a longer story that because I had a finite time, I didn't want to go into, but I can tell you more. Not only supersymmetry, but actually general coordinate invariance is in a sense broken here. In the effective theory, what happens as you look at the expansion of the effective theory in the lower dimension, you have a Pauli-Fierz leading term with massless gravity, tech, and then as you expand out in powers of xi0, you're going to have a cubic term in xi0. Those integrals are all nice and finite. All the higher order corrections you're going to get to infinite powers of xi0 are finite. They're nice because I had Chris Erickson, you can actually do the integrals. So you do the cubic integral. And then you see, this is what the kappa, it's normalizable, by the way, and you can see the kappa that you get, the effective gravitational coupling constant. So you say that comes from the cubic term in h mu nu cubed. And then you come to the quartic term, and there's a nice finite coefficient that comes from that. But you say, wait a minute, we go back to Arnowit, Deser, and Miesner, and the expansions, and I know what I anticipate for the quartic term. Let's see if it's the number that I get agrees with the number I expect from the cubic term. No, it's not. It's a funny number. It's not the right number. So we looked at this in an example. What's happening is it's remembering the higher dimensional theory. What is there is this kind of spontaneous breaking of diffeomorphism invariance because you're sitting on this background and expanding around it. You would only start seeing this at four graviton interactions, which I think there are not too many experiments on at present. Although maybe it's interesting whether you can see any of this in black holes. You start to realize that the relevant symmetry that you see in the effective theory actually is the full higher dimensional symmetry starts to express it because it isn't a consistent reduction. The higher dimensional theory is still there, but you have to either hit things very hard or you have to go to high order before you start to see this. I mentioned about diffeomorphism invariance because surely the same thing is going to happen for supersymmetry. Actually, by this technique, it breaks to n equals 0. I don't know if you wanted n equals 1. Well, I gave you a little bit more. Okay.
Well, I mean, I don't know. Nowadays, n equals 0 is better.
N equals 0 is definitely better. Now, so this is starting to suggest all sorts of, maybe you can kill this. Of course, that's supposed to be, the real test of science. With an idea like this, these non-compact situations, can you genuinely kill it? And I haven't tried putting this into observational constraints. But you can start to see interesting things you can try. Obviously, there are no 4 graviton scattering to date, but maybe on a black hole. Another thing that's hard, the trouble is it gets mathematically hard because of all these special functions. Can you, first of all, find a black hole in the lower dimensional theory in order to try to start seeing some of these questions. There should be one. There should be one, but are you going to be lucky enough to actually get an analytical expression for it? I don't know.